Welcome to another episode of Wearing Flip-Flops. I'm Ron, and with me, Yaron. Hi, Yaron.
Hey, guys.
Today we wanted to do something different and start with a quiz. Yaron, can you indulge us?
Yeah, so we thought today, starting a little bit differently, I'm going to play a song for you on my acoustic guitar, and your job is to identify the song, to guess the song name. So I can give you a quick hint that it is somehow related to today's topic. So let's see if you can detect the song name.
Well, let's see the recording. Go for it. Not bad, Yaron. Not bad.
Thank you so much.
For those of you who managed to guess that, that's great. Shelve it for a moment. We'll be right back in a couple of slides with the answer. But before that, I wanted to talk about something else. Keyboards. So the keyboard layout that we are all used to today is called QWERTY because of the letters QWERTY, fly. But back in 1936, there was a different layout called Dvorak. And the difference between those two was how the letters were set on the keyboard. In the Dvorak, which was designed for speed and comfort, and you can type much faster and don't get fatigued. Most of the letters that are widely used were on the home run, which was the center line where your fingers are. On the QWERTY, on the other hand, it was designed to prevent mechanical typewriter jams, so it was less about the human and more about the machine. So we have here, two types of keyboards. One is much better for speed and comfort, and the other is much better for the machine. And one of them won. Let's see those, side by side.
Yeah, and the one that won was not the one that was better. Let's put it this way. As we all know, we are still using the QWERTY layout most of the times here. And when we look at the reasons why, part of it is because of timing. So the Dvorak layout came along in the Great Depression era, not a really good time for people to make capital investments. And
changes, right?
Yeah, and a few years later, there was World War II. Again, not a good time. People prioritized reliability over experimental technologies. And there's also the notion that technology has to be 10x better in order to really proliferate. And nobody wanted to invest something like 100 hours of training just to switch to a different type of keyboard. So QWERTY is still around.
Yeah. So we had the good enough. We had a lot of typewriting machines that were already QWERTY, and making a change was a big investment. And there was also the gap of most of the people did not know well to type on Dvorak, and they were just used to the QWERTY keyboard. So keep that in mind also, because it is tied to our topic today. And back to the song that you played so nicely. So for those of you who guessed the song name, go buy yourself something nice. For the rest of us, the song name is The Winner Loses. It was out in 1992, and that's by Body Count. So it's a great rock ballad. And we also wanted to thank Tiberiu for bringing this topic out. Tiberiu, you asked us to talk about the downfall of Specman and E-language, and I'm not sure yet whether it's the Dvorak or the QWERTY, but we'll talk about that in a minute. So yeah, that's about that.
And now for our special guest for the show. Today we have Chico Tzadik. He's one of the really the verification experts out there for a long time. He probably doesn't know it, but I went to his Specman class 23 years ago as a junior verification engineer from National Semiconductor. I remember it.
Great to have you here. Thank you so much for coming.
Thanks for joining. It's a pleasure. And really, Chico is one of the experts on methodology and languages, Specman, SystemVerilog, and maybe Chico, maybe you can introduce yourself quickly, and when we can dive in.
Okay, my name is Yecheskel Tzadik, but everybody called me Chico. This is the nickname that my sister gave me when I was very young. Anyway, I graduated university at 76, meaning I'm about 50 years in this business. I started as a board design engineer at the beginning, and then I decided that I like software better. I moved to software, and from there, I went to a silicon company named National Semiconductors, and I was the head of the software group there at that time.
It sounds like everyone started from National Semiconductor. At least everyone on today's podcast.
Yeah, it was a great company at that time in Israel, but it disappeared eventually. Anyway, and then we start. I was moved from my job as a software engineer into the verification because we had a lot of bugs and problems in the chip that we taped out. And from there, I kind of fall in love with this topic, and I stayed there for a while. I was about 13 years in National Semiconductor, and then I joined a startup company called Verisity, which actually invented Specman as a language, as a tool, and the language E as a verification language. I was a VP R&D from day one, and I quit right before the IPO. I was exhausted from many hours of work, and
Great
since
timing.
then I went. Yeah. And then I went to Intel, where I continue working on verification methodology definition, and I worked both in Specman for about half the time, and then in UVM about half the time, and I was stayed there until last year. And in the last year, I'm trying to do some methodology improvement at Nvidia Israel.
Let's dive right into questions that we were asked to ask you. And the first question that comes to mind is productivity numbers. You use both Specman and UVM on kind of similar designs. So you're one of the few people I think in the world that has the perspective of the good and the bad for both. So can you share with the audience the difference between those and some productivity numbers?
Well, Specman was the first verification language that came out, and then later on it's actually the same company, Verisity, actually invented the OVM, and from there the UVM. As such, it is a language which is targeted for verification. That's why all the construct and all the infrastructure, the development environment was really, from the early beginning, was aimed for verification. And I think eventually it became a best fit for what we need for verification, and even UVM with all the consortium behind it and so forth are getting closer every time to Specman, but I don't think they can reach the richness and capability that Specman provide for verification.
If you have to sanitize the essence of what's different, what's different?
Specman has two main capabilities that rare and very few languages in the world really use that. One of them is the aspect-oriented capability, and the second one was the capability of running at the same time some of the code is compiled to native machine, as you are running your simulation on, and some can be run interpreted, meaning that when you run a test in verification, you can load a test environment that knows how to control the device under test, inputting and output and so forth, and even checking it. But for the stimuli, you want the test to actually change each time you run a different test, change the scenarios that are injected. So, and
can you say a few words about what is aspect-oriented?
Aspect-oriented enable one person to actually extend a struct type without inheritance. It means that I can go to any struct that is defined in the verification system and add to it, whether this is data or whether this is a constraint for a random generation, or even modify method. You can extend method, you can replace method, you can add code in the beginning of the method or end of the method. The reason this is very important for verification is because the concept of separation between test environment, which can do anything under configuration, but has to get information from a test file, which is outside. So the test file extends those structs that need to be configured, and in the same file you can change many of such struct and method and change the behavior of the test environment according to the needs. Okay.
And if we're talking about UVM, what do you need to do there in order to reach, the same capabilities?
There is a capability in UVM called factory, which is a kind of a pattern that a lot of languages use. You call a factory and you ask it to give you a kind of a copy of the struct extended type, and then use that instead of the original definition of the struct. Meaning that in the same compilation runtime, you actually maintain two types of struct in the memory, which first of all, it's much more complex to do physically, to do the work in coding. And secondly, it takes a lot more memory to actually do that.
So can you talk a bit about the productivity numbers? How many more lines of code? How much more debug effort? What's the difference in productivity with Specman compared to UVM?
Last time I measured it was about, 5 or 6 years ago. It was about factor of 2 in a lot of areas. This has to do because of the AOP and the interpretation, as I told you. This come together, by the way. If you if really support good AOP, you need capability of interpretation to do that. And that's a number I measured in some of the projects. I didn't really had a chance to duplicate the work in both languages many times, but in those situations where we convert from one to another, these are the numbers that I basically got.
I'm just curious if, from your perspective, is there any advantage or something interesting in the SystemVerilog UVM ecosystem that is better than the Specman and ERM ecosystem, or?
Well, it's hard to say. I mean, let me say this. I think anything that you can do in Specman, you can also do in UVM eventually. The real question is how many lines of code and effort you want to invest. So anything that I said, including the AOP, is with the factory, is kind of provide a solution to UVM. So you can't say that you can't do it. The real issue is how many lines of code eventually you're going to maintain.
And how many bugs you're going to introduce when you write the factory code and, all the macros and, right.
There is any kind of rule of thumb that I know about the how many lines of code, if you count them in 10K lines quantities, it goes exponentially. So and verification environment today are over 1 million lines of code on an average. Okay, so think about it. If I even add 30% more, it's a lot of maintenance resources that require just maintain it alive. Not to say that the needs to change it from project to project, enhancement, according to the device under test, right?
Yeah, actually, it's a great point. Even 30% when you talk about millions is quite a lot. Can we dive into some specific examples? Like let's talk about an environment or a test that you had in the past from your experience. Let's dive into something that is worth comparing. What did you do here with Specman? What did you do there with UVM? And let's try to quantify and better understand. You say I'm 2x or 30%, or let's try to understand the notion of what's required to do in Specman or in UVM in order to achieve the same.
There are constructs. Specman actually is a programming language like all the object-oriented the programming language, and UVM is also such, right? Except that
just a question before. Sorry for that. I think in order to compare apples to apples, so I would have compared Specman to SystemVerilog and UVM to ERM, or kind of the libraries on top, or do you think differently?
I think ERM and UVM are the same, and basically, again, it's the implementation and the lines of code that they use. Methodology-wise, I think it's the same, provide the same capability, the same way of doing verification, which is right, I think. And the only issue, again, is lines of code and maintenance cost. Okay, but let me give you an example. You wanted an example, but I think the best example is the maintenance of the test. If do a test in SystemVerilog, it's much more complex without the AOP and interpretation. Okay, the way that we work with Specman, we compile the whole environment without the test and use it many times for different tests. The tests themselves are E-code that using AOP extend different structs within the test environment and configure them, add to them functionality that is required, whether this functionality is for specific additional feature in the new project, or whether this is something that you rarely run. For instance, you don't have to collect coverage during all the period of developing the project, right? You might start kind of a little bit later, somewhere in the middle of the project. So this kind of thing are fitted very, very nicely to AOP. What AOP provides is ability to add an interpreted file that add a feature. If you don't add this file, for instance, the coverage file, you don't collect coverage and so forth. To get the same thing with UVM, you have to always compile the whole thing, and with switches, you configure it not to use the code. But you do pay for memory and runtime, and the more important things, you pay for complexity, okay? So it's much harder to do changes, small changes in the environment without breaking the whole system this way. If you keep the test bench to the minimal required for running a basic test, and then everything else is additional interpreted code, it's much easier to actually maintain such an environment. Okay.
But it does come with some challenges, right? I mean, you can sometimes, if you're not very strict with the methodology of what you extend and what you do in the test, sometimes you can break things or create a very convoluted code.
Absolutely, you're absolutely right. And it has to come with very strict methodologies, that's first off. And secondly, I think that the industry kind of thinks that verification is a work of hardware engineers, But I think with these two languages, software engineer, especially by E, I think software engineer or software capability of your engineers is very, very important to succeed. And you can always get to a bad usage of AOP in such a way that you will not be able to maintain the environment anymore. It becomes too complex. I think that you hit it exactly the caveat of Specman and the E language. I mean, it is very strong, but it is complex, and in some areas it's kind of give you a rope to hang yourself. Okay.
Right. With strength comes responsibility, right? You have to be responsible and not write, garbage code or something that will look at it 6 months later and nobody's going to understand.
Exactly. So, Chico, if I can gently sense, it seems like you favor Specman in a way. Why do you think Specman isn't as popular as UVM today?
We already mentioned one thing. I mean, it is complex and it is dangerous if you are not using the right methodology and the right educated people that can use it correctly. While UVM is from the outside of it, it looks like C++. So it's a language that every engineer, whether hardware or software or computer engineers, really learns in the university. It's much easier to learn. It's much easier for people to understand when they join a company, a newly joined company. They can understand what they see much easier. Just ramping up on Specman and the E language takes a few months more than actually ramping up on UVM. So the complexity is something that managers need to pay attention for, and it's dependent what outside engineer you have in your area. I mean, if there is a lot of other company using Specman, you probably will be able to hire an experienced Specman programmers out there. And if you are not in this situation, I suggest you get off of Specman and use UVM, because the chances that you find engineers that with the knowledge of UVM is much higher, I think.
Thank you. Actually, in that aspect, I think, Yaron and myself both, our careers split. I went to Cadence and Yaron went to Synopsys. So for many years, we were kind of competitors. Rivals, and rivals in a way. And, it was interesting to see the dynamics where Specman, at the time, as you mentioned, really had the upper hand, because it allowed to do things faster with less code. But for some period of time, it was proprietary. And then Synopsys came with, a great play of, pushing and driving the SystemVerilog and the UVM. And then it became a dynamics of, companies that loved Specman and companies that, due to many reasons, worked with Synopsys on UVM. And even though at the end of the day, Specman became a standard, not everybody, went and implemented it all. So it became, if you want Specman, you should probably work with Cadence or on top of, VCS, unless you're working with Cadence. And, I think it was a brilliant marketing act, together with, challenges that we had at the time with, what's the right thing to do at Cadence, and more, critical mass, as you mentioned, of design verification engineers went to the UVM. So today, if you want to hire Specman people, it's difficult. It's not as easy as, you mentioned UVM being taught at the university. So there was time where you, Chico, were teaching Specman, and it was taught in a lot of forums. Nowadays, less and less people are taught Specman. So I think in addition to the technical challenges that you discussed, that is also, another angle that could be, a business and an ecosystem reason to why this happens.
I agree. I think this is a situation. I think even Cadence today, in some area they neglect Specman. For instance, AI, they develop a lot of the tool that is based on AI, support just the UVM from Cadence, not the Specman. So it looks like that even Cadence kind of planning for the future to actually, I don't know if they drop Specman eventually, but they put more
I don't think so. Yeah. I don't think so. It is a great language, but it's kind of pushed aside. But a question that we wanted to ask you, if you were, to start a new verification project today, having said, everything that we just discussed now, which language would you have chosen, and why?
I will choose very SVTB, the UVM Verilog, from now, because of the practical reason that you mentioned so far. It will be much easier for me to actually do a tape out if I'm a startup company, or even company with breadth years of experience. Still, if this is a new project, I would move to UVM, or maybe even jump directly to AI sometimes in the future. So if you really start a new project, you better consider using AI as the basis. And once you use AI, these two languages cannot beat with it. With the capabilities that I see today.
Let's talk about that. Let's expand on that stuff.
That's probably going to be very interesting to our listeners.
I think that it will be possible in the near future to actually extract all the data during simulation that is required for verification and put it in some certain database. And from there, you can ask the AI to look at the result of the test, compare the behavior to the spec. Okay, it will take a lot of iteration until you get the AI to answer correct question. But the nice things about AI that eventually, when you start reaching the end of the project, most of the things that the AI can do will be fairly accurate. I wouldn't say that we'll see no test benches anymore in a simulation, but the amount of codes in the test bench can be reduced significantly, and a lot of the tasks that we're doing today can be done better in AI.
So, maybe you can educate us, because not every one of our listeners is an expert in verification. When you build a verification environment, what are the components that you need to have as of today? And the right question after that would be, okay, so won't you need that? Would you skip that all? But let's start with just the base of what is there in a verification environment.
The verification environment has three parts, I think. There is a stimuli generation, which is very important. This is what stimulus activity and trying to explore the bugs. The second one is the checking mechanism. Let's talk just about end-to-end checking, for instance. It should be according to the spec. And the third one is coverage. And these are the three things that are important.
So are we giving up now with the AI on any of them?
It gradually will move to that. I think the easiest things to do is actually to start with coverage with AI, Because if you think about it, coverage is just counting information existing in a huge database. If you imagine that all the tests dump a lot of information about state machine and interfaces and clocks and events within the simulation, dump them out into a database. You just want to ask the AI to actually see that all combination of a state machine and the input to a unit were properly checked. Okay, so it's a mechanism that doesn't require the complex language definition. It just need to kind of configure the AI and what combination of states are a collision with the other combination of state machine are really important. First of all, that they can happen and that they should happen, and they are important to measure.
So just to understand the idea, you're talking about the AI looking at the spec and then generating kind of direct tests to cover specific scenarios and use cases according to the spec?
Actually, initially what I was talking is just coverage, assuming you have the whole test bench running except the collection of coverage. And you dump all the information outside and you collect the coverage by AI, okay? And the AI can come back to you and say, you didn't test this one, this combination of inputs, and this is how I would suggest that you change your test. So it will take a test which is closer to the situation that you want to get and suggest modification, and you just duplicate the test file, do the changes and do it again. In this stage, we didn't save anything. We just did a better collection of the coverage. We save a little bit about the code of on the code of the coverage, but it's not the majority. Eventually, since the AI has the capability also to read the Verilog code, okay, you can really say, I don't need random generation at all. I want to tell the AI to generate the stimuli per situation. So he instead of generating one test that randomly run a lot of combination, instead of that, it will generate a specific test that hit specific scenario. And together with the coverage, you will be able to actually generating those tests overnight and collecting the coverage again and see what holes you have again and again. So you don't need a random generation. You need just a machine that injects the stimuli into the DOT, and the stimuli are generated by the AI. That's one possible direction.
And how do you check that the stimuli and the DOT actually behaved correctly?
This is the hard part. Okay, the hard part is actually making the AI understand the connection between specs themselves, which are written in simple user language, human language like English, understand the spec to a certain extent that given a situation or a flow of inputs, it can tell you at the end what should be the output on the other side. This is the hard part. I think this will take time. I think that in the first stage, what we will need to do, we'll need to ask him to use existing reference model that we have in the test bench, and he will use those reference model to tell him what is correct and incorrect as an output, but he will do the rest.
Chico, may I ask, what do you, or how do you spend your time today with AI? What do you play with? What's working? What's not?
Currently, I would say is just doing some simple task But it does help a lot in verification. Most of the tasks, I would say, are something that somebody or a verification engineer could have done with some complex script. So that's the level of how we use AI today. For instance, let's say you want to understand what's happened in specific test. The AI can read the log files, and you can tell him what went wrong compared to other tests. Or please compare it to all the 100 tests that we have on the disk. Compare this particular test, why this test failed and the other didn't fail. And it gives you just the differences in the way he look at it. For a human to do that, it's a lot of work. And by the time you get to, I don't know, to the 100 tests, you forget what you saw, right? While AI machine doesn't care. It can look at that and give you exactly what is the assets that could be potentially the reason that this test failed.
So to mirror my understanding, if I understood correctly what you're saying, it's not yet debugging it all. You just not ask it what's wrong and it tells you, but it does flags differences and things to go and discover yourself.
I think this is where the market, where what I see that people are capable of doing today with AI. Of course, it's eventually going to grow and the capability going to grow, but it's still in a level, I would say, that people may write script that can do that, but maybe not as accurate and as good as AI, but it could have been done. And still, it's a lot of help in a lot of things. So it's more like investigations, I would say. Even if not related to tests, if somebody is new to a test bench and want to ask a question, who is accessing this field? Who is driving the value? Who is looking at this field? You can do it with graphs, right? But it's much more accurate if you ask the AI and then ask him to actually go to the root cause of the change, okay? Which is not easy to do. So you can do a lot of learning, a lot of the investigation with AI. If you want to do a global modification, I want to generate a subset of my test environment for certain things. You want to tell him just build let's say a small test environment just does this stimuli, okay? This kind of stimuli. It can take out all the files which are not necessary and modify those who left and build you a small test environment. But this is where we are today, okay?
So does that mean that unlike, let's say, the past 20 years, this opens up the opportunity for people who are not really verification engineers to start doing very sophisticated stuff if somebody builds the AI ecosystem for them? And maybe even they will not need to code, not SystemVerilog and not Specman at some point.
I think this is where we are going, yeah. I think the validation engineer will be the one with more, I would say, the controller, the brain behind the machine to say this is important, this is not, this is correct, and this is not. And while the stage of inferration is still going on, a lot of resources will be invented in that. But eventually, toward the end of the project, you will see good result, I think.
Thank you.
Yeah.
Thank you, Chico. I think our time is almost up. Anything you guys want to share or conclude?
I would summarize the whole discussion was about Specman and UVM. I would say that if you are already using Specman, don't drop it until the AI come and replace it. And if you start a new one, you either take the chance and jump on the AI wagon right now, or start with UVM for a while and consider jumping to AI once the AI really maturity is proven. One thing about the AI that people need to remember that sometimes you get false alarms, okay, with AI, and you cannot draw a absolute 100% safe conclusion from what the AI tells you. So initially, at least in this stage, test benches will stay just as a backup for the AI until it's really
And it gets better. Yeah.
Until we have at least, I don't know, a few thousands tape outs that are safe, nobody is going to take the risk of taping out something that is not 100%.
My take on, we called this chapter "The Winner Loses," and we talked about the benefits of Specman and how it should have been a winner, but it kind of lost to UVM. And again, if we're looking at AI, it seems like UVM may lose to AI, and time will tell. We'll see that. But anyway, Chico, it was a pleasure having you here. Thank you for joining us, and see you all on the next episode. Bye bye.